Hello, everybody. Welcome back. I hope once more that when you are listening to this video, you are all safe at your homes. Okay. And I hope it stays that way. And we'll continue these lectures as long as we have to. And I hope you have listened to the lectures that I've recorded and already posted, and all of you have received the emails that I have sent. So now we want to move on to another important topic. Again, going back to your book, it's in the chapter 5 towards the end, is deals with failures of materials. Before we go back to failures, I want to have a quick recap, okay, about a couple of things. So now remember the stress tensor that we were dealing with. So we had this stress tensor, which we know exists at every point in a given body. But when this stress tensor has to be evaluated, you have to specify the exact exact reference frame for you to evaluate that. So even though the stress tensor exists as an abstract quantity, in order to evaluate it numerically, you need to decide which reference frame you will be using, right? Because the components of the stress tensor will be calculated as per the orientation of the reference frame. And so the components need to be calculated as per the current orientation, and to give the relationship between the stresses in different directions at a given point, we had the very important equation called the equation of transformation of stress, right? So we had the equations of transformation of stress. For example, one of the equations was if you have sigma xx, so the new sigma xx in the rotated frame is given as half of sigma xx plus sigma yy plus half of sigma xx minus sigma yy. There's a cosine theta here, sorry, 2 theta here, and a sigma xy sine of 2 theta. Right? This is one of the equations. Similarly, there are other ones. I'm not going to write down all of them. Now, in order to find, for example, in this case, we know that there will be a particular angle or inclination at which sigma xx dash will find a maxima, right? So now to find this maxima, we would have set d sigma xx this by d theta equal to 0. And this for us leads to the condition that tan 2 theta, maybe I just put 1 because there was another theta I'll discuss in a minute. We had sigma xy, sigma xx minus sigma yy by 2. Okay. So I think this is the correct one. You can just double check the notes once again. Now, between 0 to 360 degrees, there are actually two orientations of theta, one of which will give you the maximum stress and the other will give you the minimum uniaxial stress. So, and we had also shown that on planes where you have this maximum and minimum normal stresses, the shear stresses are absent. So there are no shear stresses on those planes. So those particular planes, so were called the principal stresses, right? So principal normal stresses occur when normal stresses attain a maxima or a minima. So we'll just say maximum or minimum values, right, in this case. Now for the shear stresses, we had to, if you had to find the maximum or the minimum shear stresses, so for maximum slash minimum shear stresses, you can do a similar calculation, and what you will find is that tan 2 theta 2 is, it is very similar to the previous relationship, except that you have sigma xx minus sigma yy here divided by sigma xy. Right? So it's very similar to this, and it turns out that theta 1 and theta 2, they are oriented at 90 degrees to each other, right? And where the maximum shear stresses occur, there the normal stresses need not be 0. Okay. So these were the two important directions in a two-dimensional state of stress. So by the way, I forgot to mention, I think, that this is only for two-dimensional states of stress. Yeah. So we'll need this later on, and so this was just the recap I wanted to do for today, and we'll need it later on and when we are discussing some of the failure theories. So I just wanted to do this recap. Okay, so that brings us to the important point, which is what we want to discuss, the yield and failure criteria. Before we even begin, I want to sort of warn you that this is actually a very complicated area, and this is complicated because, see, the yield and the failure criteria, they depend on the particular type of material and the constitutive relationship that governs the material. So we come up with an understanding of how yield and failure occur in a certain, say, given type of material, but the moment you change the material to some other one where the constitutive relationships are very different and the material is structured very differently at the molecular scale, all your understanding actually just goes out of the window and you have to bring it all over again. Yet, nonetheless, the fact remains that the important or the most commonly found building blocks that we use are something that have remained sort of constant for a long time. Of course, there are these new age materials, new type of manufacturing techniques that are coming up, 3D printing, this and that and whatnot. But still, despite all that, we still have the predominance of metals when it comes to building bridges, for example. We still have the predominance of concrete, etc., when it comes to building houses. So that is why still understanding of the older theories for the classical materials, in a sense, if I have to say, that makes sense. So before we do this, we must understand what we mean by failure. Okay. Now this is a very complicated term because failure can mean a lot of things. It's not a very quantitative term because failure in some senses is subjective. You set up a device or you set up a machinery with a certain objective, and the moment that objective is no longer being met, then failure has occurred, right? So a loaded structural assembly can be regarded as having failed when it is unsuitable for intended use. And this lack of suitability can occur in many ways. So there are many different modes of failure, right? So when it comes to modes of failure, so there are many different ways in which material can fail. For example, of course, you can have yielding, for example. So there's a little bit of, let's say, plastic behavior that the material is encountering. The strain is no longer purely elastic in nature and it cannot be recovered. So then there's a plastic deformation that has occurred. That yielding can be regarded as failure in some cases. Of course, something like fracture would definitely be regarded as an important failure, because in almost none of the cases that you can imagine you'd want fracture in a given material. Similarly, even excessive elastic deformation, deflection, can be thought of as failure. For example, you are building a bridge and the bridge moves so much that it just throws your vehicle off balance. That is not something that can be that is sustainable in an engineering design. So excessive elastic deflection can also be there. You can have large deflection from instabilities, okay, and I think I don't know if I'm forgetting anything here. So there's one more thing. So instabilities. So for example, buckling, which we will not do too much in this course, but we'll try to touch upon at the end. Instabilities can also be regarded as a failure mode, because most of the time you do not want to have an instability, and the reason you don't want to have it is because it starts extremely suddenly and it's very difficult to control after that. So these are the different modes of failure, and whenever we are talking of failure, we typically, so these are the first two are the important ones, the yielding behavior and the fracture. These are something that we want to focus on. And when it comes to this, these two, it is important to specify the kind of material that is undergoing either yielding or fracture. And usually the materials, when we have to classify them, they are usually classified either as, so in this particular regard, I am talking about yielding and fracture primarily here. The materials are generally classified as brittle or ductile. Okay. These are very important and old classifications. You probably have already heard of these two terms by this time, because they are often used in even general literature, and you probably have a very good intuitive understanding already of what these terms mean. But we'll discuss this in a little bit more detail here. So for example, material failure is typically classified under ductile or brittle. Okay. In ductile failure, an appreciable amount of yielding occurs before failure happens. Okay. So appreciable amount of failure sorry. Appreciable amount of, what am I writing? Not appreciable amount of failure. Appreciable amount of yielding before failure. I don't have space, so I'm not going to write that. So what I mean, it's appreciable amount of yielding occurs before failure. And what are good examples of that? Examples, of course, are metals. These are the classical example. Metals are considered as highly ductile materials. Sometimes, for example, cast iron may be brittle, but in general, things like brass, copper, etc., they or steel would fall under the ductile category. Brittle materials are materials where small yielding before fracture before fracture occurs. Okay, and examples of this would be glass, for example, uh, concrete, ceramics, okay, etc. Again, these entire discussion, appreciable, what is appreciable, what is small, this is very qualitative, right? So why don't we put a little bit of quantitative spin to this? And the way to do that would be, just take a look at the stress strain diagram. Okay, and let's say I'm going to draw it for one particular material. So there is one material which comes up like this, and somewhere here it fails. Okay, and so there is another material which goes something like this, and this ending point is the failure, okay, or the fracture. So here, this is fracture. So can you tell from these two graphs which is the brittle material, which is the ductile? It should be so obvious given what we were just discussing. This material right here, this is your brittle material. This is the curve for a brittle material. So you see, you have a more or less linear increase. There's some amount of yielding that has happened right here towards the top, and then it fractures very, very quickly. The other material, this particular one, the second line, the red line, this is for a ductile material. Okay, and you may have a situation where yielding, for example, for both these ductile materials and the brittle material may occur around the same value. But from this quantitative, say this graph, you can see that the ductile material can probably absorb more energy before it fails than the brittle one. So the brittle one, although it has a yield strength maybe, which is very similar to that of the ductile material, but the total amount of energy that goes on into the system, the total amount of energy, when I say that, it is essentially, I'm referring to this area under this graph. So this is for the area for the brittle material, whereas if you were to look at, let's say, the ductile material, then this is the energy under the graph, the area under the graph. And this is often called, this area under the graph, this is also called, this is not a very good color, this is also called the modulus of toughness. often denoted as UT. And this basically, this toughness defines the ability of the material to absorb energy prior to fracture. Okay. So this is something that so this area under this stress strain diagram represents the density of the strain energy absorbed by the material prior to fracture. So this is a very, very important quantity often. Now I am sure that you should have seen so if you want to do a quick experiment in your home, a simple ductile, something which behaves like a brittle material, which behaves like a ductile material would be, let's say, plastic. And something that behaves like a brittle material, biscuit. It breaks very quickly. And in this regard, I just wanted to share an interesting anecdote or an important part of history. This is a photo from Hampi. When this photo has been clicked by me, so it belongs to me. And so this is a temple in the background. It's a huge ground if you ever happen to go, and you'll have to travel quite a bit by foot from any of these areas. The part that I want to show, I don't know if you have, any of you have had the ability to visit Hampi and understand how these temples were built, because if you look around Hampi, there isn't much of a construction material, but what you have are just rocks. So this entire place is very, very rocky. You can see these rock mounds, right? And all these hills right here, these are very, very, very rocky places. So how were these temples made? They were all made using these bricks. And I'm sorry, all made using these rocks. Did I say bricks? If I did, sorry, that's a mistake. All of these temples were made using these rocks. So all these places are rocky, and these huge mounds of rock that were there, they were broken up and they were used to make these temples. Now these rocks, the reason I'm talking about this is it's an excellent example of a brittle material. And one of the things that they pioneered in India was the art of brittle fracture. Okay, so for example, the exact thing that I want to show you is, do you see this very beautiful rock right here that has a, can you see how plain this particular face is? It's almost as if this has been cut, but it has not been cut. It has been fractured across this. And the way this rock has been fractured, you can see that this was part of something probably bigger, and it has been fractured. Is, if I enlarge this photograph, do you see these small grooves that are here? Okay, let me undo that. Yeah. So I hope you can see these small grooves right here. And what they used to do is they used to make these small grooves, and they would put a wooden block in these grooves, and they would put hot water over them. And because of the hot water, the wood would expand and it would cause a local stress. I hope you are able to now recall the lecture that we had last time on stress concentration. So there would be a massive stress concentration here because of these grooves and the wooden blocks that were expanding, and that would cause a stress that would cause fracture in this entire material. The fracture would initiate here, and because it's a brittle material, the entire thing would just fracture all at once. You can see that they were trying, maybe some student was doing it right here. Do you see these grooves? These are all these small grooves were made for doing this kind of a fracture, and you can see this all over. So I hope next time you go to Hampi, you take some time off and you see how brittle fracture played such an important role in creating this historical place. Okay. Now another important another important concept that you must understand before we go into the theories of fracture is something called creep. Okay, sorry. This is too thin for my liking. I like this slightly. is the idea of creep. Okay? This creep is not a person. He is. It is just a phenomena, and creep is defined as straining. It's a time dependent phenomena, so I'll just put time dependent. I'll show you why it is time dependent in a second. Straining of a material under constant stress. Okay. So what does creep mean? Again, that's a very qualitative write-up. Let me just specify that. So I'll just draw two graphs side by side. Actually, just a second. I need more space for the other one. Okay, so let's say okay, so now let's say this is stress versus time and this is strain versus time. So let's say one day you go into the lab and you have decided to take a certain type of material, whatever this material is, and then you have decided to apply a known amount of stress to this. Let's say that is sigma naught. And then, so this is stuck to a wall, and then you are just going to measure the deflection at this end. So this will obviously, there will be some strain in the material. So when you go, and if this is an elastic body, then what will happen is that you will have a strain. This is some sigma naught. So this is your handbook in which you are just making notes. So you are doing this particular experiment, and then you say, okay, I have put, this is my control, I have put this much amount of stress into the system, and what are you going to register for an elastic body? What you are going to see is some constant strain that is going to come up, right? So this is going to be epsilon naught. So immediately there will be an instantaneous, the moment this is an instantaneous increase in stress, so you will register an instantaneous increase in strain, but then nothing else will happen. So the strain remains constant with respect to time. But then, so if this is a metal, then this experiment is probably happening in, you've done this for a few minutes and then you've left. Let's say you forgot this weight on this body, on this metal, and you have left and you've gone for a vacation and you have come back after 2 months in the lab. Do you expect to see the same strain value? No, what will end up happening in that case is you had the initial experiment. So now I have to draw, I'll draw one more diagram right here. Okay. So you had done this initial, you had noted that this goes up and it remains constant. Now my time axis shrinks because this was few minutes here. Maybe I'm just writing few minutes. This is just an example, and now it has been a few months, right? So the time axis has sort of changed. This is but become enlarged. So now what you see is that this was the initial plot you had, and let's say there is somebody there who's this a robot which is measuring your strain value. What you'll see is that this has now increased, And for a long time, maybe for a week or two, this did remain constant. But then after that, even under a constant stress, the strain kept on increasing. So this is your strain on the y-axis, and it has now started to increase. And if you've left this for a very long time, maybe a few years, you come back and you will see that this is ruptured. This phenomena where the strain increases under a constant stress, that is called creep. So when it says straining time dependent of a material under constant stress. So the straining is this phenomena right here in this graph, and it is happening under constant stress, and it is a time dependent phenomena. Yeah. So this is a very important phenomena which happens in systems, and it's not usually part of a undergraduate course, but the full analysis of this is not part of an undergraduate course, but this is something that you must be familiar with. This curve is also often given the name J. Usually it's a function of time, it's also a function of the initial stress, and this is also called, the J is also called the creep response function. So this is a very important function right here, and this is forms part of what is also called the creep test, and the creep test happens to be a very important quantification. Of material properties. Okay, so what we want to do is, we are not going to so we want to understand failure, and that's why I was giving you a sort of a bird's eye view of failure in these kind of systems. And we looked at the modes of failure, and we said we'll focus only on yield and fracture. And there are two different type of materials, as I said, ductile and brittle, which are important categories for us. So we will be discussing ductile brittle, and we give ourselves a bit of a quantitative understanding of what ductile and brittle materials are. And then I also described to you a phenomena called creep. And this is just going to be an introductory part, and we'll leave it at this, because the failure theories that we are going to encounter will not have time as a parameter. So they will all be static, but you must know that when we are discussing these failures, which I will do in the next lecture, these failures are static failures. They're not the time dependent failures. There are other types of failures which are time dependent, which are not going to be covered as part of the course. We will only focus on the static failures. Okay, so we will pick up from here in the next class. So I'll leave it here now, and okay, take care people. We'll pick up from this in the next class.